In this talk, I will present an application of a transfer learning approach in a railway scenario. These research activities have been conducted in the context of the Shift to Rail project RAIS, whose main objective is to investigate how to bring AI approaches in the rail sector and provide recommendations for their implementation in railway applications. Information about Rails can be found on the public website as well as by following the project on LinkedIn and Twitter. The purpose of this study is also to promote the potentials of transfer learning in the rail sector, especially in those scenarios where only a limited amount of data is available. Indeed, the lack of suitable data is one of the main obstacles to be overcome for the take-up of data-driven AI-based technologies. I will briefly introduce transfer learning and present an application to level crossings by discussing how data were collected, the adopted transfer learning approach, and the obtained results. This specific application has been suggested by Hitachi Rail STS, leading company in the rail transportation industry, which is also one of the advisory board members of the Rails project. Conceptually, transfer learning aims at reusing the knowledge acquired to solve a given task in a specific domain, namely the source task and the source domain, to address a similar or a different problem in the same or another domain, namely the target task and the target domain. The main advantage lies in the fact that by reusing knowledge, it is possible to obtain competitive results even with a limited amount of data. Transfer learning has been already widely applied to address different tasks such as image classification by exploiting well-known datasets such as ImageNet, and in different domains including avionics, road transport, and railways. At a high level, we can identify 3 transfer learning strategies. However, given the limited amount of time, I've just reported a table showing which kind of strategy is most suitable given the combination of the source and target domains and tasks and the data labels availability. We used an inductive approach. In particular, we were interested in transferring the features representation learned in the source domain to our task. In this case, as described in the picture, we reused the same feature extractor of the deep learning model that was used to solve the source task. Then we built a new classifier on top of that feature extractor. Notably, at this point, it is possible to proceed by freezing the weights or fine-tuning them. The freezing approach expects that the network will not modify the weights related to the feature extractor during the training phase, but it will learn only those belonging to the classifier. Differently, the fine-tuning approach expects that the pre-trained weights are used only to initialize the network's weights, and thus they will be modified during the learning process. Our case study focuses on rail level crossing, which is an important topic in the rail sector. We address level crossings maintenance applications by leveraging non-intrusive sensors to understand how this application can be improved by applying artificial intelligence approach, specifically deep learning. This case study comes from 2 main reasons. And the first phase has emerged from one of the most recent analyses conducted by the European Union Agency for Railways. Fatalities from level crossing accidents account for about 30% of all the fatalities registered in railway scenarios. Therefore, they are widely studied and used to define benchmarks for different purposes. Secondly, we aim at exploiting non-intrusive sensors. Many systems, especially those safety critical as level crossings, must undergo specific certification processes. The compliance to those certifications might be invalidated by an intrusive approach, resulting in a reapproval process that may be very time-consuming and expensive. In addition, we are including all the possible level crossings, even the oldest ones that may not be equipped with the latest technologies and sensors. Microphones and cameras represent a suitable solution, as they could be installed externally and easy to maintain, as well as they can provide useful data. Analyzing level crossings at a high level, we could identify 3 macro components: the alert bell, the light signal, and the gate arm, which must work properly together to ensure safe operability. We are developing an architecture composed of 3 AI-based modules, each of which supervises one of the components. In particular, this talk focuses on the level crossing alert bell detection system. Since acoustic sensors are mature, non-intrusive, and robust, they are good candidates for large monitoring functions. Therefore, we aim at assessing the correct functioning of a level crossing alert bell by implementing a deep learning-based model for sound analysis. The aim is to build a model capable of recognizing the level crossing alert bell sound. However, to the best of our knowledge, no dataset containing such kinds of audios is available online. Additionally, level crossings are widespread in many scenarios characterized by different kinds of sounds. For instance, in cities, we could find sounds such as car alarms, car horns, and ambulance sirens, which may be easily confused with a level crossing alert. Lastly, it would have been very time-consuming to build a large dataset to train a deep learning model from scratch. To address these issues, we built a dataset composed of audio samples belonging to 3 classes: level crossing alert bell, no alarm, and generic alarm, to improve the robustness of the model. And then we adopted a transfer learning approach by reusing an already existing network whose pre-trained weights are available online. These solutions allowed us to both collect only a limited amount of data and build a model capable of recognizing a ringing alarm and classifying it in LC alert bell and generic alarm with good performances. As said before, our dataset contains 3 classes. The level crossing alert bell, indicated as AB, the no alarm class, indicated as NA, which encompasses city and countryside background noises, such as passing cars, wind, rain, and so on, and the generic alarm class, indicated as GE, which encompasses all the disturbing alarms, such as emergency vehicles, car alarms, and so on. LC and NA samples were collected by leveraging the YouTube platform. Differently, the GI samples were obtained by exploiting the audioset dataset, which is available online and contains about 2 million of 10-second audios. The samples in the audioset dataset are organized according to an ontology including 527 different labels, and each audio is associated with one or multiple labels. However, we selected only 19 of them related to the samples we defined as disturbing alarms, and manually checked the samples to remove some possible outliers. For example, those characterized by heavy background noises. At the end of the data collection process, we obtained 1,197 audios, most of which has a duration of 10 seconds. However, it is important to underline that these acquisitions have been captured on the field by YouTube users, but they have different intensities and have been collected through various devices. So, since we did not perform a precise on-site acquisition, features like devices versus decibels are not addressed in the study. This point will be addressed in a second phase. Since with our limited number of data, it would have been quite difficult to properly characterize a complex deep learning model, as thousands or millions of samples are typically required, we decided to further exploit the research conducted on the audioset dataset. Indeed, audioset data are provided in 2 formats, as wave audios and as 128-dimensional audio features. These features were extracted by using a VGG-like network named VGGish, which was pre-trained on a preliminary version of the YouTube 8M dataset. Since the authors made the pre-trained weights available, we decided to exploit the VGGish to build our classifier. Therefore, we reused the convolutional blocks, those in the red box, and replaced the fully connected layers with a new classifier. Notably, for the following analysis, we loaded the pre-trained weights of the convolutional blocks and froze them not to allow them to vary during the training process. Practically, we reused these convolutional blocks as a pure feature extractor. When adopting a transfer learning approach, it is a common procedure to pre-process the data for the target task in the same way the source data were pre-processed to solve the source task. This is due to the fact that, conceptually, the learned weights are able to detect the characteristics present in a particular representation of the data. Therefore, we adopted the same data preprocessing proposed by the VGG authors. So, starting from the WAV files, we normalized the inputs and converted the audios from stereo to mono. Then we performed the resampling and computed the log-mail spectrogram. Lastly, the spectrogram was partitioned into different frames, each of which represents about 1 second of the original audio. So from 10 seconds audio, we extracted 10 frames. To each frame, we associated the same label of the audio. However, the first frame, as in this case, but also the last frame, may not be representative of the class. Therefore, we decided to trim these frames from each audio sample in the training dataset. Eventually, we obtained 2 datasets, an audio level dataset and a frame level one. The table above shows the subdivision of this dataset into training, validation, and test set. The trimmed column under the frame level is related to the training set obtained after the trimming process. Lastly, joined represents the dataset obtained by merging the training and validation sets, while trimmed joined is the same dataset but after the trimming operation. The latter was used to retrain the network in the test phase. The model was then trained on the frame level trimmed set. BAS was tested, but was tested on both the frame level and audio level test sets. To build our classifier, we fixed some parameters and other parameters, while we varied others to select the most suitable model. Particularly, we performed experiments by considering 1 or 2 fully connected layers with 100, 1024, 512, 256, or 128 neurons per layer. Then we also studied the behavior of the network by varying the learning rate and the batch size. Lastly, a more detailed analysis is required for the flattened layer. Typically, in a convolutional neural network, the last convolutional layer produces an output, a three-dimensional tensor that must be reshaped to be processed by the classifier. This is the purpose of the flattened layer, which has a variable number of the neurons, depending on the last transformation performed by the feature extractor. This layer is weightless and serves only to present the features extracted by the convolutional blocks to the classifier in the same way that the input layer serves only to present the data contained in the dataset to the whole network. So we performed 4 kinds of transformations to obtain different flattened layers and study the behavior of the network. After several tests, we found the configuration that performed the best in the training phase, whose parameters and hyperparameters are reported in the top left box. The charts show the accuracy and the loss trend obtained in the test phase. The red, blue, and grid lines are respectively related to the frame level trimmed joint set, the frame level test set, and the audio level test set. Notably, the accuracy at the audio level is much higher by about 6% than the accuracy at the frame level. This is due to the fact that an audio is considered correctly classified if the mean of the prediction performed of each frame matches its actual class. Practically, considering a 10 seconds audio, we have 10 frames and 10 predictions. By performing the mean of these 10 predictions, we obtain a single audio level prediction, and if this prediction matches the audio level, then the classification is considered correct. Clearly, the accuracy at the audio level is higher because the various misclassification at frame level are somehow absorbed when performing the above-mentioned mean. Taking a step back to the training phase, we can notice how transfer learning was extremely useful in this context. Here are depicted the training performances in terms of accuracy and cross-entropy losses of the same network, which is the best configuration, evaluated under 3 different conditions: weights loaded but not frozen, weights not loaded, which means that the training was performed from scratch by randomly initializing the network's weights, and weights loaded and frozen, which is the case we have discussed in this presentation. Notably, without freezing or loading the weights, the network shows an unstable behavior, which can be deducted by the multiple oscillations, especially on the validation loss, which is the blue line, the right chart of each couple of charts. This seems to validate the theoretical thesis that our dataset is not sufficiently large or sufficiently optimal to properly characterize a deep network. Differently, by freezing the parameters of the convolutional blocks, which are about 4.5 million, only 80,000 parameters belonging to the full connected layers had to be learned. These allowed us to obtain a very stable classifier, which demonstrated to have good performances, especially at the audio level. The proposed approach reveals some advantage in the rail domain. Transfer learning seems to be a suitable solution for enabling deep learning-based tasks when only limited data are available. We spend less than a month collecting data and understanding how to transfer the existing knowledge to our task, which is a relatively small period when facing such a problem. Additionally, by loading and freezing the weight, the network training time reduces drastically, from about 12 seconds to about 1 second for each epoch, as the network has to update fewer parameters during the learning phase. Also, non-intrusive sensors can be exploited to avoid possible reapproval issues and, at the same time, obtain qualitatively good data to address maintenance problems. Lastly, the availability of public video and audio sources, such as YouTube in this case, allows avoiding, at least in the developing phase, the on-site data acquisition, as this process was already performed by YouTube users. However, on-site tests are required to effectively assess the model performances. Indeed, in the very near future, we are intended to understand the correlation between the distance of the microphone sensor from the level crossing and the performances of the model. Additionally, we are also interested in understanding the motivation behind a possible misclassification. Wanting to hypothesize a real case, a level crossing alert might be misclassified only because its intensity is very low. But this could mean that even the road users might not hear it. Therefore, maintenance activities are required. To conclude, as discussed at the beginning, we aim at building a complex system capable of analyzing and detecting level crossings abnormal behaviors to assess the potentials of artificial intelligence for level crossings maintenance applications. So, thank you for your attention.